Hi everyone, welcome to my presentation, Database Reliability Engineering for MySQL. Um, my name is Matthias Crauwels. I'm presenting to you from Belgium. Currently I'm a principal consultant in Pythian's OSDB group. I have a bachelor's degree in computer science. I've been using and administrating Linux machines for as long as I can remember, over 25 years now. And I've been involved with MySQL for over 10 years. As a principal consultant, I'm mostly focused on MySQL at Pythian, but we also support other technologies. This is something about the company and all the problems that we see in our customer base, and then these are the places where we can help our customers. As you can see, we do consulting, managed services, we do migrations, and also cloud solutions, as well as on-premise, as basically anything that the customer needs. When we're talking about database reliability engineering, I see four main focus areas. The first one is availability, and preferably high availability, and we'll talk about the difference between both of them. Service discovery, knowing where your services are. Observability, knowing what's going on within your databases, and then when disaster strikes, how can you recover, and can you get back up to running situation. So yeah, let's get started with the first one. So high availability. So when you look at this very average car, you see that this car has 4 wheels. Well, you can only see 3, but I can guarantee you that there's a 4th one. So what this car needs to operate, to work, is 4 wheels. If you lose one wheel, the car is not working, so it's not available. So having 4 wheels for your car is not high availability. When we're talking about high availability, we can keep the same comparison and talk about the wheels of a car. And in this case, we're talking about the bolts holding the wheel in place on the car. And in this picture, there's 5 of those bolts. And if you lose one, it doesn't mean that your car won't drive anymore. It doesn't mean that your car is not available anymore. So those 5 different bolts, they are ensuring high availability. So if you lose one, you can still operate. There's no need to, no immediate need to stop everything and to fix it. Like if you lose a wheel, then you can't ride anymore. But if you lose a bolt, then you can still ride. You can still drive. You might want to go see a mechanic to figure out why you lose a bolt. Maybe it wasn't tightened enough on the last maintenance, and so then it's a human error. Or maybe there's something structural wrong on the car that the bolts are loosening, and so you need to see a mechanic to figure out why and to try and fix it. But this is the difference between availability and high availability. If we now go back to the database, because we're here to talk about MySQL, when do we consider MySQL available? So in most cases, you will need just one server to write transactions, which is your primary, or used to be called the master. And then you need at least one server to read transactions from. In the worst case, you can use both the same server for both operations. But in many cases, when you have a very large scale website or application, you're gonna need more than one read server, and this is what we need to have availability for MySQL. So high availability in that case means that we make sure that we can keep the database available even when a server fails. So this is your general topology. You have one primary, one writer server on top. taking all the writes, and then you have a bunch of read servers on the bottom where you can do read scale out for your applications. And in this case, the master is a single point of failure. So if your writer server fails, no more writes can happen to the database, and your application will be down, or at least have some kind of degradation, because you won't be able to write. Imagine a service like Twitter. You can probably still read all the existing tweets, but you cannot send a new one. So that would be a problem for many people. So in order to prevent this single server to be a single point of failure, we will introduce a topology management tool to handle these kinds of failures. And so the tool that we will introduce is called Orchestrator. And Orchestrator is a high availability and replication management tool. You can use it for all kinds of purposes in your MySQL environment. If you connect it, you can use it for discovery. And so what this will do is, if you give Orchestrator the coordinates of one of the servers, it will start using the regular DBA commands like show slave host, show process list, show slave status to try and connect to the other servers in the topology. And that way it will discover the entire topology by just feeding it one single server. One requirement is it needs to be able to connect. If it can't connect, it can't run the commands I'm listing here. So you need your automation when you spin up a new server to create the Orchestrator topology user, so Orchestrator can connect to the database to figure out where the topology fits. And then the very nice and very useful feature that Orchestrator has is the visualization, the web UI. So when it discovers all those servers, it will present them to you in a very nicely formed web UI, which you see an example from here. This is from the Orchestrator manual. And as you can see, there's different colors in the servers. You have the orange, green, blue, red ones. So these designate different data centers. So this topology is an anonymized topology. There's no specifics about these servers. Like you can see that they're 5.7, but not the minor version. You cannot see their host name. You can see their replication delay, but nothing more than that. So that's also a feature of Orchestrator. If you want to create screenshots of your topology, you can anonymize them to make sure that you don't expose too much information about your environment. And then the third and probably most useful feature of Orchestrator is the ability to refactor. So what we understand by refactoring the topology is making changes, like pointing a replica to a new master, or promote a new server to become the new master or the new primary, or do things like start stop a replica, do some maintenance on the binary logs. All of those things are things that Orchestrator knows about and that it can help you with. So there's a command line tool that you can use. There's an API where you can script a lot of things, or there's the web UI where you can do drag and drop. So you can basically drag one server to another location in the topology, and Orchestrator should be able to figure out how to reconfigure replications so it can handle the change. There's some prerequisites for that, obviously, but in general, Orchestrator can do that to almost any topology running MySQL. And then all of these things, they are extremely nice, but if if your master goes down or your primary goes down in the middle of the night, and you get paged to go log into Orchestrator and do the drag and drop, or to run a script, to do the promotion, you're not going to be happy. What Orchestrator can also do is it can automate the recovery. So you don't have to get up, so it can automatically figure out, hey, the master is down, I need to create a new master and recover the topology. To do this, first of all, the detection of the failure is a requirement. And so if you think your typical monitoring tools like Nagios, Zynga, those kind of tools, they will send probes. So they probe the master or the primary, and what do when they detect the failure? So imagine your monitoring tool tries to connect to your primary, and it cannot. What do? Do you take immediate action? It might be like there's a network failure between the monitoring tool and the database. Will you retry maybe to see if there's actually a problem, or if the monitoring was having like a temporary failure, or and if you retry, how many times will you retry? So all of those things are items you have to think about when setting up automation. The advantage that Orchestrator has, it's connected to every server in the topology, and it can gather information from all of those instances. So if it detects a problem on the primary, it will check with all the replicas of that primary, like, hey, can you still see that primary? If you can see the primary, then there's no problem. Then I have a detection issue, and I won't take any action. But if all the other replicas are saying, hey, we can't talk to our primary, we don't get any binary log events anymore, then Orchestrator can be fairly certain that there's a problem, an actual problem with the primary, and it can use that knowledge to make decisions and to do a promotion on the first detection. And this is what Orchestrator calls the holistic approach to monitoring, instead of an individual server by server approach. And so back to our example, so we had the situation on the left where our writer went down, and so what Orchestrator will do is it will take one of those readers, make it a new writer, reattach all the remaining readers to the new writer server, and take the old writer out of the cluster. So it will put that server aside. Something went wrong with that server. It might be as simple as like a network glitch, and at that point you can say, okay, this server is healthy and we can put it back in topology, but it needs a human to look at it, to investigate what happened. And to prevent for all reader servers from being promoted to master, and every time the master being put aside, there is an anti-flapping mechanism built in Orchestrator. By default, it will not make a new promotion within the hour. So what you might want to do is send some kind of alert that someone needs to check on what happened to that old writer. Make sure that it gets back into the pool of available servers, and figure out and acknowledge that everything is fine on the new topology. So to do this, if you run a single Orchestrator node, obviously your Orchestrator will be the single point of failure. So since Orchestrator 3.x, there's an implementation of the raft consensus protocol in Orchestrator, which allows Orchestrator to be set up in an HA way. Well, you could set up Orchestrator as an HA system before, but then you needed like HA on the database side, and Orchestrator cannot manage its own backend database because it needs that to be functional. So if that database would have gone down, then Orchestrator would be down. So what we used to do before Orchestrator Raft was like set up a synchronous replication backend, or virtually synchronous, like Galera or these days InnoDB cluster, which is still available. But if you use the raft protocol, then you can you can drop that replication component from the database on the database layer, and you can even use SQLite if you have a small scale implementation. You can use SQLite as the Orchestrator backend. So you don't have to manage any other database server technology for Orchestrator itself. So Raft will do leader election and distribution of the data as mentioned, and in order to have an HA setup you need at least 3 nodes. If you have 1 node you never have high availability. If 1 node goes down there's not another one to take over, so never HA. If you have only 2, then they can start, if they lose connectivity to each other, they can start fighting which one is the active part, and so you need a majority vote, so you need 50% plus 1, so you need at least 3 nodes for a high availability. So if two nodes lose connectivity, that one node say, hey, I'm a minority, so I will be I will decommission myself for now until I can rejoin the cluster, while the other part can still be fully functional and operational. So this is what it looks like then. Before, with the synchronous replication backend, you had the replication of the data on the database layer, and there was no communication between the nodes. If every node was connected to the clusters, which also had some implications. While in the Raft version, you see that the communication is happening between the application nodes. There's one leader node taking making the calls on the servers, and the other 2 are passive. They're monitoring, but they're following the lead of the leader node, and there's no more replication between the different backend databases. So that brings us to the next section, and that concludes the part of high availability. So brings us to service discovery. So service discovery is the ability for application to know where the writer server is, where the reader server are, where the reader servers are, and there's several options for this. I've known installations where if the master changed, there was a deploy required to deploy the new configuration file, and then the application would start writing to the new server. This works, but this is not the most convenient way, because it needs someone to trigger that deploy or read it automatically, or the other option is to have a DNS change. In that case, you're relying on an external system. DNS is something that's probably not managed by the database team. And there's a famous Belgian blog that says everything's a freaking DNS problem. So I'm not a big fan of DNS. It's useful, but to rely on, I'm not a big fan. Floating or virtual IPs, they're also an option. In many cases, this will mean that your virtual IP is only available in a single data center, or you have to route your IP addresses to multiple data centers and then make sure that it's bound to the right one. This is a problem probably when you have a data center issue and you need to fail over to a different data center. Then virtual IPs are much more troublesome to migrate. Or the final option, and this is what we will be discussing further, is to use a proxy server, something to sit in the middle between the database and the application. And in this case, we'll be talking about ProxySQL. ProxySQL is a layer 7 application proxy. It's layer 7 because it's not just network throughput or not network relaying like something like HA proxy. What ProxySQL does, it accepts the client connection, and then based on its configuration, it will send traffic to MySQL servers wherever it's configured to send it to. So it's intelligent. It can be used for multiple databases, multiple clusters. It's built on the MySQL protocol, so it can understand the traffic that passes through it, and it can do things like splitting reads from writes. It also understands the database topology underneath, so it knows whether instances are up or down, whether replication is fine, whether there's replication delay. It can even do something like GTID consistent reads, so it can make sure that the connection is only sent to a replica whenever the GTID it's requiring to be there is actually applied there. So it's very knowledgeable about the MySQL topology, and it can do very intelligent routing, and basically it protects the application from the complexity of the database technology. So from application from the application side, what it sees one server where it can connect to, and it sends a query and it gets a result. But underneath that one server, there might be tens or hundreds of MySQL servers serving the traffic. So it's a very convenient way to protect the application from that kind of complexity. To start, some terminology. So in ProxySQL, we speak about host groups, which is basically a group of backend servers where queries will be sent to. Very important to know is if you send queries to a specific host group, the query will be sent to only one server within the same group. It will not be sent to all the servers in the group, just to one. This is to load balance between multiple servers. Query rules are like the core functionality for ProxySQL. That this is what defines where a certain query or query type or a query for a certain user needs to be sent to. So that is where you define how the traffic will flow through your proxy. And then MySQL users and servers, these are items that the proxy needs to know where to send traffic to. So the server configuration is actually the list of MySQL servers that is available in a certain host group. And then the users are also required because the proxy will connect, the application will connect into the proxy, so it needs to authenticate to the proxy, so the proxy needs to know the users and the passwords in order to validate those credentials. And then from there on, depending on the user or the type of query or the query text or the address or the port you're connecting to, traffic is sent to the right backend server by evaluating the query rules. And then the basic design for ProxySQL is very simple. You have your application servers connected to your proxy, and then the proxy connects to the database on the backend. And then I see people think like, hey Matthias, but now you have a single point of failure on your proxy. Correct. But this green ProxySQL block can be multiple proxy servers, and you can basically load balance them using like a general stateless HTTP load balancer or something similar, or TCP load balancer in this case mostly, because the proxy can be clustered to share configuration. So you have multiple proxies that will distribute the configuration among each other, and then the application can basically choose which of the proxies they use, because they will all have the same configuration, and they will send the read and the write traffic to the same backend groups. Another approach is this, where you put the ProxySQL instance on the application server. So basically your application connects to localhost, and the proxy then again sends traffic to the right backend group. This works very fine also with the clustering of the proxy. In many cases, what is being done, if you have a lot of proxies, a lot of application servers, is you make a combination of both of them. You basically put the ProxySQL servers as some kind of satellite servers on the application side, and you put in the middle, you put a layer of proxy servers which do your core routing. So basically your satellite servers, they will send traffic to your core servers, and your core servers will send traffic to your database backends. That's usually the most most high available way to set up ProxySQL without the need of any additional load balancing applications or something. So that really helps. That brings us to the observability part of this presentation. So what is observability? So the first thing in observability is you need to know if your systems currently are having an issue. So you want to be alerted for problems. Like if your disk is running out of space, you want to know about this. There's many ways to alert. You can use a pager system, you can use an IM system or email. Depending on how reliable your IM or your email is, you can be satisfied with the performance of that, or you can have some kind of pager system like Opsgenie or PagerDuty or something like that to send you alerts on your phone, so you know when there's an issue. And then the other part of observability is when you need to troubleshoot performance, or when you're diagnosing an issue. You want to have some kind of graphical interface where you can have dashboards with metrics, so you can compare against the past situation, like, hey, my database is suddenly going slow. What's different in the workload against last week? So last week everything was fine, and now everything is slow. So how can we see what's ongoing? So that's what observability is about. And what we typically use when our customers don't have a good solution for this is Percona's monitoring and management tool called PMM. This is a all-in-one solution for observability, and it's mostly focused for databases. It's free and open source. It consists out of, I have a slide for that, out of several open source components. And it's an out-of-the-box solution for monitoring MySQL, Postgres, Mongo, ProxySQL, Linux servers. It will be able to be your full monitoring and alerting stack when you configure it well. The caveat that I always tell to our customers is that this is a single server, so it's a single point of failure. There's currently no real good solution to make PMM high available. But in general, it's not mission critical for your application. So it's not if your observability stack is down that your applications will be down. It's gonna be important to not have it down and to keep it running, but it's so you can know what's going on, but it's not gonna be of that disaster kind that everything will be down, your revenue will be stopped. So that's generally not the case. PMM is available as a Docker container, as a virtual machine image, or as an AWS AMI. So whenever the easiest installation way is to use the Docker container. So you basically install Docker on your favorite OS, and then you do Docker pull PMM server and Docker run PMM server, and you'll be up and running. The VM image also works but you'll need the virtualization team to approve that image to be loaded. And in AWS you can always use the AMI, which is a convenient way to spin up an EC2 instance for PMM. So these are the components. In general, you have a PMM server component, which is what we've been talking about so far. And then you have a PMM client, which basically runs in general on your database server. So this client has two tools to configure PMM admin and PMM agent. PMM admin is the tool that you use to write configuration into the server, and the PMM agent is the tool that ensures communication between all the components, and that will make sure that the right exporters are being started. So exporters are things that collect the metrics from your system. You have the most basic one is the node exporter, which is basically exporting information about your system, your OS. You have the MySQL D exporter, MongoDB exporter, Postgres exporter, ProxySQL exporter, and then the RDS exporter. If you want to monitor RDS, the RDS exporter then uses CloudWatch and enhanced monitoring in CloudWatch to pull system level metrics from your RDS, because you cannot install the PM client on the RDS machine because you don't have shell access. So in this case you need to install it on a different machine, which can be the PMM server but doesn't have to be the PMM server. But in many cases this is how it's done, to install the exporters or the client then on the server, to be able to collect metrics from the managed service database. On the PMM server itself, you have a big component called Victoria Metrics, which is a drop-in replacement for Prometheus. The difference between Prometheus and Victoria Metrics is mostly that Victoria Metrics supports push and pull model. So Prometheus only supports pull model, so it pulls metrics from the database server. So the monitoring server needs to be able to connect into the database server to pull metrics out. And in many cases, this connectivity into the database server is considered to be like a security hole, because you don't want anything to connect into your database. You want things to be pushed out from there. So that is why this is what I believe that made Percona switch from Prometheus to Victoria Metrics. And then you have the PMM managed daemon, which is the management tool that configures all the systems that are being monitored, and it uses a Postgres backend to store all of that data. On the other hand, you have the query analytics part of PMM, which connects to the database using either using a slow query log file or using the performance schema if it's enabled. And the query analytics are not stored in Victoria Metrics because Victoria Metrics is mostly a time series database. The query analytics are stored in ClickHouse, which is a column store database, which is very good for analytical workflows like finding aggregates and finding like the bad queries that consume the most time. You can use ClickHouse, and then there's a little query analytics app that is running in Grafana on the PMM server, that you can use then to explore the data stored in ClickHouse. And then Grafana is the tool that mostly exposes the metrics and the dashboards. So you have some screenshots here. The PMM login screen, something about the operating system here, like this is overall CPU utilization. This is a MySQL summary with connections, supported connections, client thread activity, all those kinds of things. And then here you have a screenshot of the query analytics, so you can see all the queries that are running. You can filter on environment, on cluster, on database name. So it's a very useful and powerful tool to know what's going on in your system and to start diagnosing issues. In the latest versions, there's also an alerting option. It's a bit out of scope for this session, but know that in the later versions of PMM, you can also use it to set up alerting, and so you based on the metrics that it collects, it can send you alerts. So, but this is out of scope for this session. So, and then the final part of database reliability engineering is disaster recovery. And disaster recovery is mostly what do you do when a catastrophic event or a human error hit your database. And there's two major factors in disaster recovery, and they're called RTO and RPO. The RPO is the point in time where you restore your service to. So in the in the graph here on the bottom, you see this is the time when disaster hits, and so the RPO is the time you need to go back to get to a point in time where you can have a consistent restore of all your data. And so the amount of data lost is the RPO. So this is the amount of data you can lose in the event of a catastrophic event or a human error happening. And then the RTO is the recovery time object. It's the time that you can be down before you can restore your service. And typically, if you want to have less downtime, you might lose more data because you basically restore an older backup, and you'll go back to that point in time, or you promote a delayed replica to become the new primary, and you start using the data as it was on that delayed replica. But mostly we try to limit the amount of data we lose, and we get a little more downtime to get to a more consistent, more reliable way for disaster recovery. And so RTO, the fastest way to get to a stable situation again is with disk snapshots. So if you want to make consistent snapshots of your data, you need to stop MySQL cleanly and then make a snapshot of the disk, or you run flush tables with read log and you freeze the file system for a moment. All of these operations, all of these options, they are invasive to MySQL. If you stop MySQL, it cannot serve traffic, so you need to run these on a special replica. But this is the fastest way to get a consistent copy of the data, and from that snapshot you can immediately spin up a new server and be going with a consistent data set. Another way to get to make a backup of MySQL is Percona Xtrabackup. This is a way to do online non-blocking backups for InnoDB. InnoDB is important here because it relies on the MVCC options that InnoDB offers to create the backup. So if you want to make a backup of my ISAM table, it doesn't have those features. So in order to make a consistent backup of my ISAM, you need to block all the traffic and make the backup of my ISAM, and then you can release the database again. So for my ISAM, Xtrabackup is still blocking, but the recommendation is to use InnoDB for almost all workflows, so that should not be a problem. It can do full and incremental backups. It's what we call a physical backup. It's just like a snapshot option. It takes a copy of the data on disk, but it takes a bit longer than a snapshot. Snapshot typically runs within seconds, while Xtrabackup depends on the size of the database to run. And very important is, if you want to use Xtrabackup, make sure that your Xtrabackup and your MySQL version are in sync, because there was a problem a while ago where there was a change in the redo log format of MySQL in one release to the other, and all the backups started failing. So important is, before you do your MySQL upgrades, make sure that you have a working Xtrabackup version before upgrading. So then point-in-time recovery. This is a way to reduce your RPO, your data loss, to 0. If your binary logs are backed up and available next to your general backups like Snapshot or Xtrabackup or whatever backup method you use, you can reduce your RPO to 0. Obviously, doing that takes time, so the RTO will never be 0 in this case. Well, RTO will never be 0, but it will be increased if you want to do point-in-time recovery. And in order to be able to do that, is you need to live stream your binary logs to a backup location. So when disaster hits, you can still have access to the binary logs, and you can figure out from the binary logs the exact point in time where the catastrophic event or the human error or whatever happened, and you can replay the bin logs, the binary logs, until that exact point in time, so you don't lose any data from your event. But to do that, obviously that takes time. So, conclusion. In order to have high availability and in order to have database reliability, MySQL replication is required. If you have a single server without replication, you can never achieve high availability. You can never achieve database reliability. That's a no-brainer. Orchestrator is a tool that can help you to automate your writer availability. Orchestrator will not help you for reader availability. Reader availability you need to solve by scaling. You need to have some spare servers available that can be used during an outage of one of the servers. If a reader server fails, that should not affect your database availability. That should be absorbed by the other servers in the topology. If a writer server fails, Orchestrator can help to promote a new writer server, but that takes away one of the reader servers. So you need to be able to deal with those kind of events. ProxySQL can really help with service discovery, especially in the mixed mode where you have a core proxy and you have the satellite proxies on the application servers. It will be very easy for your application servers to figure out where the database is, and the proxy clustering will make sure that all these nodes are in sync and can be used for talking to the right database. PMM, if you don't have any monitoring tools for your databases, it's that easy to install. It's very user friendly. So I highly recommend, if you don't have anything good, or if you're not certain about what you currently have for your metrics and monitoring, I highly recommend to install PMM, to expose the environment metrics, to set up some alerting, and to be able to troubleshoot performance when it happens. And then obviously when disaster strikes, backups are always important. Make sure to make backups, make sure to test backups, because otherwise you'll shoot yourself in the foot. And that's all I have for today. So if you have any questions, feel free to ask through the channels that are available. I will be online to answer some of the questions. If you do not have any questions at this time, but if you want to reach out to me, here's my email and my Twitter. So you can always feel free to contact me if you have any questions. And that's it. So thank you for watching, and until next time.